All right, physics class, as promised, I am working through one of the example problems from the reading. The one I chose is example 4-11 from page 86. So to save a little bit of time, I went ahead and wrote down some of the basics. I drew a diagram, which is typically what I do. Remember, when in doubt, draw it out. I drew a diagram of what's going on. If you read the example, it talks about a box being dragged across a surface, a horizontal surface, but the force is being exerted at an angle. And it asks us to find the acceleration and the normal force acting on the object. So one of the first steps that I suggest is to draw things out. Another step that is strongly suggested that you really should be following on these is include a free body diagram. So that's what I'm going to do next. So free body diagram, again, I don't have to get cute, I don't have to get fancy. I'm just going to use a box to represent the item, in this case, appropriately enough, a box. And that box is being pulled by an applied force of 40 newtons at 30 degrees. In addition to that, the surface that the box is sitting on, be it a desk or whatever, is exerting a normal force upward, and at the same time, gravity is exerting a downward force on it. Now, what's the purpose of doing that? Remember, we do the free body diagram to help us with our force summation. In this case, though, I've got motion happening, or I shouldn't say motion, but I've got forces happening in two different dimensions. So this means that I've got to break down my force summations, and I'm going to actually do two separate force summations now. I'm going to do one force summation in the y-axis. I'm going to do another one in the x-axis. Let's take a look at the y-axis first. In the y-axis, remember, according to Newton's second law, the net force acting on an object, in this case in the y direction, is equal to the mass of the object times the acceleration of it. In this particular case, recall that this object is being dragged across a horizontal surface. It's not accelerating either up or down. So I know that the acceleration of this object in the y direction is 0. And now I have to account for all of the forces acting on that object in the y direction. And for the purposes of this one, I'm going to consider up to be positive, down to be negative. So I'm going to start with any forces that are acting in the upward direction, because those that, as I've said, I've already determined that's going to be the positive direction for me. So in this case, I see that the normal force is being exerted upwards. And in addition, I also have to account for the fact that, see how that applied force is being applied at an angle? There's a portion of that force that is going to be in the horizontal direction, but there's a portion of that force that's going to be in the vertical direction. So I have to account for that. The entire applied force is not in the vertical direction, so I can only account for, or I will only account for, the portion that is in the vertical. Since my angle is there, the component of the vertical component of the force is opposite of that angle. So going by SOHCAHTOA, I need to use the sine of the angle to get just that vertical portion of the force. Then I've got one more force acting in the y direction, and that's the force of gravity. So since that's in the downward direction that I've already determined is negative, I'm going to make that, or I'm going to subtract that from my sum, from my summation. So now I've accounted for all of the forces, in this case 3, acting in the y direction. There's no vertical acceleration, so I'm setting that equal to 0 according to Newton's second law. Now I'm going to shift my focus to the x direction, to the horizontal direction. All right, again, according to Newton's second law, force is mass times acceleration, this time in the x direction. This time I do have an acceleration in the x direction because I only have a portion of one force that's exerted in the x direction. I already know that these are going to be unbalanced forces. There's nothing over here to balance it off. So I know there's going to be an acceleration. And that acceleration is going to be equal to the horizontal component. If we go back and take a look at this horizontal component here of the original applied force. So in this case, it's going to be the applied force times, and since the component I'm looking for is adjacent to the angle, SOHCAHTOA tells me that it's going to be the cosine of the angle. So now, going back to our original mission here, we need to find the acceleration. Well, the only acceleration is happening in the x direction. And then we need to find the normal force. Well, the normal force is happening in the y direction. So when I come back down here, for part A, I'm being asked to find the acceleration. There's my unknown. By the way, I'm still following my guesswork. Notice how I included all of my givens in my original diagram. So I don't need to relist everything. So all of my givens are listed. There's my unknown. Now it's time to set up my equation according to Newton's second law of motion. So in the x direction, the sum of the forces acting on that object, the net force acting on that object, is causing that mass to accelerate, and it's caused by just the horizontal portion of the applied force. In this case, I'm being asked to solve for the acceleration. So now, once I've listed the equation, now I'm going to go ahead and solve. So to do that, I need to divide mass by both sides, or on both sides. So I end up with that divided by that. Then, so guesswork, G-U-E-S, and then the second S is solve. All right, or I should say solve. The second S is substitute now. So now I'm going to substitute in all the values that I know. I know that the applied force is 40.0 newtons. I know that it's the cosine of an angle of 30.0 degrees. That's going to be divided by a mass of, looking at my givens, 10.0 kilograms. When I do all that, plug and chug through the calculator, I should get an answer of 3.46 meters per second squared. All right, so there's part A. Part B asked us to find the normal force. Now you might say, well, Mr. Mason, you told us that the normal force is the reaction to the force of gravity at an object. And that's true, but in this case, since a part of that applied force is pulling up, it's in essence removing some of that normal force away from the table has to exert less force upwards to keep that object sitting on the tabletop. So our upward force is actually a combination of the normal force and the vertical part of that applied force, according to my force summation. So I go back down here. I'm going to go ahead and just very quickly relist my force summation in the y direction. The net force is equal to mass times acceleration in the y direction, which in this case is 0, because it's not it's accelerating neither up nor down. It's not accelerating at all, actually. And then that net force is due to the normal force pulling up, the vertical component of the applied force, and in the other direction, the force of gravity. In this case, I'm being asked to find the normal force. So now it's time. Now I've got my equation listed. It's time to solve. So I get that over on the left. Do a little bit of algebra. So let's see. I'm going to have to add that and then subtract the applied force in that direction. Now that I've solved, now it's time to substitute. All right, so 10 kilograms times 9.8 meters per second squared minus the applied force of 40.0 newtons at an angle of 30.0 degrees. And when I plug all that in the calculator and solve it out, I should get an answer of 78 newtons.